Alright, time for another draftphysics.com, debatephysics.com, also video presentation and such. So I was going to make a photon video, because I sort of was on the subject with the last video, but this has got me curious. A dispar video on negative momentum. That somehow there's such a thing that you could subtract, that somehow there's a true canceling of energy somewhere, momentum. And obviously I'm arguing that no, conservation means you actually have to conserve all momentum no matter what direction it is. Anyway, but related is these latest group of experiments he's done, and I've been thinking about it, and I'm going to call bullshit for another reason. But anyway, he says there's no goddamn parallax problem. So he's taking an image of the same thing. I'm saying it's the same event. And he's taking the image from two different camera locations, and he's saying there's no parallax problem. It's impossible to say that, so the video is goddamn shit. Okay, so I'm not even going to watch it, because bullshit is all I'm calling. You can't evade it. Even if you had a decent camera, you couldn't evade the parallax problem. Alright, so the problem with this whole experiment, I did state it before, is when was it declared that rubber bands are, what's the problem here, good scales? So you could just stretch a rubber band between 2 points, and we don't even know how firm these points are, how much they bend. So the scale is being controlled by more than one variable. But the whole idea that you put pressure on a rubber band and this is proportional. That is, 1 pound moves it this far, 2 pounds is this far, 3 pounds is this far, 4 pounds. That obeys Hooke's law. And I was thinking about it. I'm saying, well, I don't know enough off the top of my head geometry to say, well, wait a minute, that's not really possible. All right, so let's just say the rubber band is here. So you could make a circle, okay, from the center. And you could argue that, okay, that circle is the part of the rubber band that's not stretched, and the only part that's getting stretched is this little part here, technically, okay, because you're just changing the direction. And if I change that vector to some other line, it doesn't appear to me that the this distance, okay, here, is going to be proportional, to this distance. Necessarily. So that's the question. Is it really linear? So, this isn't that challenging a test for him to do, is to take his device and orient it in such a way where he can just put the masses on and see if they actually measure, okay, properly. There's actually a scale that works. So it's really not asking too much that before you do one of these experiments telling me you have a scale that works, that you actually test the scale to see if it works. That 4 pounds is 4 units of distance, and three units of mass is 3 units of distance. You should be able to establish that first as a minimum, and they don't do any of that, which just indicates a lack of thought about how to be careful doing an experiment, and that's not their goal. Alright, so anyway, that being said, let's play this thing. Draft science conspiracy against negative direction. Conspiracy? It's not a conspiracy, so let's, I might as well draw it first. Alright, so there's basically, look, their own physics already concedes the argument. So if I was to crash two clay objects into each other, and they had opposite directions, okay, nobody believes that when they collide, their energies cancel. Okay, what they're going to argue is that the clay will deform, change shape, and that all of the energy of the two objects will be in some form of motion, okay, that will essentially cause heat, all right, and it'll be radiated as heat. So it'll go back into the environment. So let's say this had 150 momentum and this one had 50 momentum. there would be 200 momentum of heat. That would be, that's the conservation of the motion. And there's no way you could create a circumstance where you can say, okay, well, if I make these things elastic, okay, that somehow now I've changed the rules, okay, and I don't have to conserve. I don't have to account for every bit of movement, the 50 here and the 150 here. So you could have the same circumstance. Let's just make the 150 on this side for a change. And, they're not going to cancel. The 100, right, 50 plus 50 off of this one isn't going to just cancel, okay, like it's gone. And all I'm going to get is 100 come out this way. That's not conserving the actual motion in the universe. You have to conserve all of the motion. You can't play some game that, I canceled the 100 of it. Like here, there's 200 of heat, okay, not 100 of heat. Okay, there's 200. There's 200 worth of denting and deformation. So if they were dentable objects, you'd understand that the collision in here, okay, is going to total the 200. If I put something in here, it's going to get crushed 200 worth. There's no other option. All of the energy has to be consumed. Well, obviously, in that case, frankly, it's going to move in this direction, the whole thing. So, there's no way to, you can't do that experiment where it stays where it is with those uneven momentums. But anyway, so the point is that you can't, direction doesn't matter. Now, the key experiment that demonstrates direction doesn't matter is something as simple as the lever, where, yes, you drop a mass in here, put a mass over on this other side, equal distance, and you'll get almost all of your energy back, 90-some% of your energy, and all you've done is change its direction. So changing direction doesn't mean anything, and there's just no way you can have a collision between something with 100 momentums and something with 50 momentums and only get 100 out. Can't do it. And that's what they say constantly happens in the Newton's cradle between the 3 mass and the 1 mass. They're saying it creates 200 momentums going out, okay, and then the next time it hits, only 100 pops out, and then it goes 200 again, and then 100, and then 200, and then 100. Doesn't happen. Not the truth. Nonsense. Rubbish. Garbage. Silly. Stupid.
For a couple of times now, I have addressed that in collision experiments, when both objects move in the same direction after collision, both draft science model and the conventional science model predict correctly.
They're going in the same direction. I don't even know who's bothered with that experiment. No one.
This is because when both objects move in the same direction, their momenta have to be added together.
And why he's written this out, I don't know, but whatever. Yes, go ahead. So it's just momentum is a substance. It's a thing. Okay, that's the whole idea you have. That's where you destroyed Newton's insights, is you just lost the whole idea that they kind of understood this thing, even Benjamin Franklin, as an analogy to a fluid or a substance. Energy is a substance. You can't destroy the substance. You can't cancel it. It's like water hitting a surface this way. The water goes that way and the water goes that way with the same energy it had going this way.
Now, according to
the same momentum.
Conventional science, we only do this when they move in the same direction. And according to draft science, we always do this, regardless in which direction the object goes.
Yes, it doesn't matter. Energy is energy. It has to go somewhere after a collision. So after the collision, there has to be the same amount of motion, mass, mv. The mv has to be conserved because there's no such thing as a cancel. Nothing it might look like two things hit each other and stop, but they know every single time that happens, the energy has to go somewhere. So this two steel ball example is just so obvious, right? I take two steel balls and I crash them into each other. If I add the force and I force them not to bounce, I force them to stay together, they'll burn a piece of paper. Fact. The energy is not canceled. Cancel is not a thing that happens in the real physical universe.
Now, this is only the case when a bigger mass object collides into a smaller mass object. If a small mass
Yeah, it's only the case that kinetic energy is made obviously nonsense in the case where the masses are different, because you'll get a wacky kinetic energy number that has nothing to do with reality. There's no conservation.
Object collides into a big mass, the small mass moves in opposite direction after collision, and that's where both models disagree. Now here is an example where both conventional science and draft science model predict correctly.
Alright, well, this is a waste of time, right? So who cares? I don't who cares? You're going to show stuff that we agree on. Oh, well, what a waste of my time. So this whole cart thing, I already explained how he's got this 59-cent spring on these stupid carts. And the fact is that we already know now that springs don't give the energy back equally, that anytime the spring is vibrating after the experiment, that's energy that didn't get transferred to something. And if it's wobbling faster when it's pushing a lighter car and wobbling less fast when it's pushing a heavier car, it's quite obvious the spring differentially treated the objects. That is, the lighter object got less of the total energy available. So I've only repeated that now 24 times.
Momentum 1 was before the collision
such a
was
waste of my time.
0.127 for object 1. Object 2 had nothing, so the total momentum, both the textbook model and the alternative model would agree that the total momentum that we're starting with is 0.172 kilograms meters per second. And both the textbook model and the alternative model would agree with these, because both of the carts were only moving in the positive direction. If everything is moving in the positive direction...
So this whole nonsense about a positive direction, how could it possibly matter? If you concede there's no such thing as a cancel. There's no such thing as saying that I can make energy disappear. I can crash two things into each other and the energy is now not in the universe anymore. It's impossible to do that. So if you concede that simple point, then you're saying, okay, well, if 150 goes in this side and 50 goes in this side, 200 has to come out somewhere.
And the textbook model and the alternative model actually give the same predictions.
Well, why? Why are we doing this? What is this? What's the point of this? What the fuck the point? What's the point here?
Everything is moving in the positive direction.
And you're slowing it down for some reason.
Then the textbook model and the alternative model...
What the fuck? Did he do that? What the hell happened? I didn't change the speed. It says normal speed. What the fuck is going on? Did he do it on purpose?
Model actually give the same predictions.
Hooray! This proves draft science right.
Waste of my time.
This is a good experiment. Now here is draft science himself, seemingly accepting and agreeing with the results.
Oh, there's no... Why would anybody disagree? I mean, that experiment's only done 6 million times, and it doesn't involve any significant transfer mess up, because as long as you keep the masses the same, it's really simple. As soon as you change the masses, that's when this experiment gets a little more complicated. Duh. Especially with a spring. Fucker. Oh, god damn. What a waste of time.
Okay, so you can see that this did continue to move. Okay, so it still has momentum. So you can basically see that the blue cart...
And he has this slow... He slows the other shit down for no good reason. And he speeds this up for no good reason.
Post. half its light, is not going almost twice as fast. So right there, we've got a huge degrade in the amount of momentum it got. Okay, just gigantic almost. And we still have quite a bit, though, of energy left in the red card. So the red card didn't give all of its energy. It only gave a portion of it. And as he's going to state, if you really add all these up, it's okay. It's pretty consistent. You conserve the momentum. So the total momentum is conserved, because this kept going forward. Now, if it had reflected, then everything would have been a mess. But because the red card kept going forward, it means that it didn't give all of its momentum. That's why this isn't twice as high. And so you end up with pretty consistent numbers. Now, the catch is, for momentum, you conserve the momentum. The catch is, he doesn't tell you what the kinetic energy numbers are. And the fact is that the kinetic energy numbers come off 10%. All right, they lost 10% of the energy.
Well, here are the kinetic energy numbers. The initial amount of kinetic energy is 0.0264 joules. After collision, the one mass has energy of 0.0023 joules, and the other mass has energy of 0.0231 joules.
Oh, bullshit. I don't even know what the fuck your joule numbers are calculated from. I'd say right on their face, these are silly numbers, frankly. This is way too few joules. 1 joule is the impact weight of, a stick of butter dropped a meter or whatever. I think those carts could probably manage a total of 1 joule, and you got it at 0.0254. But whatever. I mean, this is just bullshit. Anytime there's a difference in the mass, you're going to have a difference in the number.
There's also going to be some loss. Anyway, however, physicist Michael will now do the collision with a small...
There you go, fucker. Why didn't you get to that in the first place, moron?
...mass into a big mass, and that's where the disagreement happens.
Taking some more data. We've got an object that is now moving in the negative direction. So just before the collision, well, there's only things moving in the positive direction. So both models would agree, if everything is moving in the positive direction, both models would agree the total initial momentum is 0.219. Again, for both of those models. In the textbook model, momentum 1, we treat that as a negative momentum. So when we're adding these momentas up, I'm going to add up negative 0.036 plus positive 0.258.
Right, so this is where we get into the simple argument that these are stupid plastic carts with metal wheels. Now, so I've pointed out the obvious, that the fact is they store a bunch of energy in the rotation of the wheels. So the higher the velocity and the lower the mass, the higher percentage of the energy is in the rotation of the wheels, not in the linear motion. So the lighter cart moving faster, its linear velocity is not its total momentum. Its total momentum is its linear velocity plus the angular momenta of the metal wheels. So when it exchanges the energy with the other cart that's going to go much slower and is much heavier, there's going to be a much lower percentage of the energy in the rotation of the wheels because they're moving much slower. And obviously there's going to be a higher percentage in the linear motion. So, fuck you again. So if all he's doing is regurgitating this physicist Michael crap from a year and a half ago. So why don't you just point out how he was going to do the Newton's cradle. He bought all the crap, he put it together, it wobbled a little too much, and that's the last we ever heard from him. The last video he made on these subjects was that, where he just disappeared. He didn't explain why he disappeared, didn't explain why he's not going to do the experiment he promised he was going to do, nothing. So just like Brozo, who promised us the lever launcher experiment, where is it? Could you answer those questions?
And I get from that point, I guess there's some rounding in here for the computer's model. I get around 0.221 or 0.222.
So there was no measurement of the actual momentum of the carts. It's only a measurement of its linear velocity, which isn't its total momentum.
Again, that alternative model claims that momentum does not care about direction. When we are adding up momentas, we're always adding up positive values. So in this case,
Look, you could watch the video. I already pointed it out that he does one experiment with the same spring compression. So he's going to launch carts with a spring. So he does one experiment with heavy carts, and then he does another experiment with lighter carts. And the two have completely different total momentums by a huge margin, like 40% difference. So a gigantic difference in the amount of energy, momentum produced by the spring. And the only explanation is, oh, okay, because you've changed how much energy is in the velocity, which means you've changed the ratio of how much energy is in the angular rotation of the axles and the wheels.
we would have to add positive.
And then you have the whole problem with the spring. Obviously, when the spring releases, this here he's using magnets. When the spring releases, as I pointed out, if the spring is still moving, obviously that's energy that didn't get into the object. And you can understand that the faster the thing that left the spring is going, the faster the spring is going to be oscillating. Undeniable fact.
0.036.
I can't believe he's regurgitating these old garbage experiments.
To positive 0.258. And I get from that 0.294. That does not give conservation of momentum. The textbook model, well, within the noise, those two momentas before and after the collision, those match up quite well. The alternative model, not looking so good.
Now at this point, draft science will turn into the most crazy conspiracy nutcase where he will do
What a waste of time this is.
whatever it takes to dismiss the evidence.
Whatever it takes to dismiss nonsense. That's right. The whole point is to find out what the mistake you're making is. The chicanery. So just like with the double slit experiment and all the lies, the preposterous lies about what actually happens, the same thing here. Did any of you consider the angular momentum of the wheels? No. Did any of you ask, why do they make plastic carts with 10-cent springs and metal wheels? Why are there metal wheels on these stupid fucking carts? Did you ever ask the question? No.
He will call the experiment a garbage experiment. Every experiment with this scenario is either crap, cheated, wrong, or extremely flawed. Something must be wrong.
I'm just saying, right on its face, I'm saying I can prove the flaw by just asking you to launch two objects that weigh only 100 grams, and then launch two objects that weigh 200 grams, and then recognize the obvious fact that the same spring compression produced two completely different amounts of momentum. So go ahead and explain how that's possible. Dumb fuck.
Dated that, and let's start taking some more data.
So now you
Well,
got
I'm not going to re-watch a bunch of this shit. I mean, I already did videos on this. This is just such old crap.
bounce back. So now his claim is going to be this bounce back gets subtracted, okay, from this exchange, not added. Okay, if you add it, it's too much energy. Now I would argue that clearly this is really high. So the argument could be made that this higher velocity, okay, of the lighter cart, in fact has more energy in the rotation of the wheels. This one has less energy.
There
in the
you
rotation
go.
of the wheels.
Guys, so I'm making the argument right there. How's he going to disprove that when they haven't even analyzed it at all? They haven't measured the mass of the wheels relative to the cart. They haven't done any damn thing. Haven't investigated it at all.
And that's making some of this up. But the fact is this one is way off momentum-wise. All right, there's lots of free momentum here, and but also the fact is if he pushes the kinetic energy button, it's also off. Okay, if you add the reverse direction, you end up being 10% too much energy, and if you subtracted it, you're 30% too little. So kinetic energy also failed to be conserved. So let's understand, momentum was not conserved, and neither was kinetic energy conserved.
Yes, momentum.
Oh, he's doing his math again, this preposterously silly difference number. Fuck you. Okay, so look, he's not going to address the point. So there's just no point. Just as they've never addressed my argument about springs. So I've been making that argument about springs for a good 6 months now. Not a single word from them conceding, yeah, springs don't give back their energy evenly. You put a light object in front of a spring, it's going to get less of the total spring's energy than if you put a heavy object in front of it. And the same is likely true for almost all explosives. Just a fact. More energy goes into heavier things than lighter things when you're using some elastic mechanism to push them. So just all bullshit. So let's see if there's anything in here. Let's see what this crap is. Yeah, I mean, really, this is old news, old hash bullshit. So I drew all the metal wheels here. So look, where's his count? He's not going to make any counter argument.
It's connected to the fact that it has received its energy from some other object where the wheels, okay, of the other object are going faster. And so they had more momentum going in than you're going to get out because you're just seeing this motion, okay? So the heavy object will look like it's going faster than technically it should because it got hit by more momentum than it appeared. So if I hit...
Okay, so here's the logic of draft science. So first of all, we have, these are the numbers taken from physicist Michael experiment. So at part 1, small mass is 558 grams. The heavy mass is 806 grams.
So yeah, it's not even good masses. They're not even double. It's not even a rational ratio.
So this one is standing still to begin with initially. The initial momentum of a small card is 0.218 momentum, right? That's what we can see. That's what we can measure. Then after collision, the heavy mass...
Yeah, we know all this. Explain to me how the wheels don't affect the experiment. Explain how it's not true that if the wheels are spinning faster, they have more momentum in them. And if they're spinning slower, they have less momentum in them. Just explain how that's not true, fucker. Or explain to me how the angular rotation of the wheels is actually in the linear velocity. Because we already know it's not. So go ahead and explain how measuring the linear velocity accounts for any motion in the wheels. That's an absolute fact that if I have a flywheel on a car and it's spinning, and I crash the car into something, the flywheel's energy is guaranteed to be part of the linear motion I could measure. That the velocity of the car includes the spinning wheel. When no, it doesn't.
Mass continues with 257 momentum, and the small mass reflects back with 0.036 momentum. Now, according to conventional science, we have to subtract these numbers. So 257 minus 36, that equals around 218. So momentum is conserved, but not for draft science, because we cannot use negative momentum. We have to add these two together. So the total momentum is 257 plus 218 plus
time.
A hidden 75 momentum in the wheels. So actually, this total momentum of the system is 218 plus 75, so 293. The initial momentum, the total initial momentum of card 1 is 293. So this 293 collides against the heavy mass, and it gives away 257, and it still is left over with 36, but going in opposite direction.
So how did he calculate the momentum in the wheels?
And it gives away 257, and its system is 218 plus 75.
So I don't know why he sped this part up either.
So 293. The initial momentum, the total initial momentum of card 1 is 293. So this 293 collides against the heavy mass, and it gives away 257, and it still is left over with 36, but going in opposite direction. So that it works out for draft science. But hang on. This one, after collision, this also has inertial rotational momentum. The heavy mass after collision also has rotational momentum. The small mass after collision also has some rotational momentum after collision. It must be. So the thing that we can measure after collision is
much less. An insanely less amount. Okay, the velocities, twice the velocity is significant. 3 or 4 or 5, 6 times the velocity is really significant. It's 6 times less.
257, but it also has some hidden momentum. Now I don't know how much.
There you go. Okay, so you don't know, you didn't really think about it, and you're just going to pretend it's not a real subject, like you always do. Like you don't have to show us that your elastic band actually measures obedient to Hooke's law.
So let's say it's around 0.020-ish. Let's just a guess. Let's take a small number, 0.020-ish. So it's what we can measure is 257, but it has
so what? He's just making a number up. Oh, okay. Fuck you.
Some hidden momentum. So let's say 0.020, and then for the small part, the thing that we can see is 0.036, but it also has some hidden momentum, 0.010, for example. So now this total momentum becomes...
All right, so we know that this one isn't, these two carts aren't going anywhere near 1/2 the speed. So, bullshit again. We know this cart's going much faster than this one. So it's 3 or 4 or 5 times the angular rotation in the wheels. Twice the velocity, twice the energy, twice the momentum. So if it's going twice as fast, you have twice as much stored energy in the wheels. And if it's going 5 times as fast, then it's 5 times as much.
257 plus 0.020, which is 277. And then this total momentum becomes 0.036 plus 10, which is 0.046. So now, the total combined momentum of both cards is, so we have...
So there's no point. You just made up fake little numbers. It doesn't mean anything.
30 momentum to the initial momentum. Because, so, we have the initial momentum, 218, plus the so-called free momentum, but then we have to take into account the extra rotational momentum for the card, the heavy card after collision, and a small card after collision. We have to include that as well into the total initial momentum. So another 30 initial momentum extra. This is kind of confusing, but I hope it makes sense. This is the logic. Now, when we reverse the scenario, instead of a small mass into a big mass, now we have a big mass colliding to a small mass. So we have the 558 grams colliding into the 308 grams. So the initial momentum before collision was 0.172. After collision, the heavy mass kept going with in the same direction with 0.051, and the smaller mass kept going or was launched with 0.119 momentum. When we add these two together, we have 170, which is very close to the initial momentum. Now, draft science, in this scenario, he didn't say anything about rotational momentum. He just saw the same numbers. All right, so we have around 170, 170. Okay, momentum is conserved, no problem.
Because there's less deception. Obviously, the heavier cart has less extra energy. So obviously it doesn't fuck up the experiment as much, and the other cart's not going to fly away at 10 times the speed. So because there's not going to be as huge a difference in the velocity, there's not going to be as big a difference in the goddamn angular rotation, dumb fuck. Oh, what an asshole. Let's jump ahead.
26, and then the...
Yeah, so he's regurgitating all of this garbage that we've already done before. These shitty experiments where you don't see a goddamn thing, horseshit, lie, nonsense, crap physics. So I'm not redoing my debunking of these garbage experiments.
Another example of a large mass hitting a smaller mass. This time the larger mass has been increased with its mass. So we have lower velocities and another mass ratio. So this one is a 400 gram card colliding into a 200 gram card. The total amount of momentum before collision was 0.100. After collision, the large mass continued with 0.037 momentum. The smaller mass continued with 0.065 momentum.
Yeah, which is close to 100, blah, blah, blah. Why are you wasting my time with this one?
Add those together and we get 102. So 100 and 102, momentum is conserved. And so once again, it doesn't matter what the mass ratios are, doesn't matter what the velocities are. We have different velocities, different mass ratios, and we still have the same momentum before and after collision. Momentum is conserved. There doesn't seem to be any difference in the amount of energy still stored in the rubber band. Doesn't matter. Momentum are conserved.
So he's using this example where both of them are hitting the rubber band's hitting another rubber band. Okay, so it's kind of a different experiment. And so the losses are a total amount of loss, and it's a real loss, so you're going to pretend it doesn't exist. Okay, I'm going to say bullshit to that. But go ahead. Make that as your argument, that it doesn't matter when I compress the rubber bands and I launch the two objects. Such bullshit. I mean, like I said, that's already been done. Physicist Michael already did it. He demonstrated it clearly by compressing the same spring compression. He shoots two heavy masses. He gets a number like 3,000. He shoots two light masses. He gets a total number of 2,000. Somehow the same spring compression produced 1,000 difference in the momentum. Bullshit.
And the heavy mass continued with 2,225. And momentum is only conserved when we subtract the numbers. When we add them together, and then we have once again free
Yeah, well,
momentum.
whatever. Again, I'm not going to continue to make the argument. I'm just saying you obviously, in all of these 350 years, you've had to produce some kind of real evidence. You've produced nothing. So that's the truth of it, okay? You don't have the experiment. You don't even have the lever showing me that the one mass only goes 1.4 the velocity. And we totally lose a third of the momentum. Every single time you use a lever, you lose a ton of momentum. And the more extreme you make the example, the more and more momentum you're losing. And even though the balance proves that, 1 pound moving 4 distance is the same as 4 pounds moving 1 velocity. Even though it balances perfectly, showing that momentum is what balances, not kinetic energies. Kinetic energies don't balance. Momentum's always balance. So you just ignore all that evidence. Ignore, again, the Mythbusters car crashes. Ignore. And again, to defend this absolute nonsense. This is their argument. They're saying that you can collide a 1 object into a 3 mass. All right. And what you can create, okay, is you put 100 in, the 3 mass isn't moving. It's just stationary, straight up and down. And then after the collision, you have 150 momentums going this way, and you have 50 going back this way. So you put 100 in, and now you have 200 going out. And then when this 150 comes back in, and this 50 comes back in, somehow only 100 pops back out. So you oscillate between having in the system 100, then 200, then back to 100, then 200, then 100, then 200. Bullshit. Okay. Can't happen. You can't destroy the motion. You can't have only 100 pieces of matter moving. Okay, let's just make the unit of movement 1. And then have 200 units of mass moving. And then have 100 units of mass moving. And then have 200 units of mass moving. Can't happen. Bullshit. Nonsense. Crap. 350 years to show me a real experiment. They have nothing. Okay, fuck this. So yeah, it was a waste of time. Oh, I guess I should have added. So when he was talking about the rubber bands and they're not, when they're colliding into each other, the two rubber bands put opposite to each other, and he's saying that the carts didn't demonstrate any losses. Well, that's because the carts can move. Okay, that's why. You put the rubber bands in a stationary condition, that is where the rubber band is in the middle, and it can't move, or the spring in this example. And so you're using a compression of a spring and then launching an object. Well, the spring is not going to able to move. It can't go somewhere. So it has to get rid of the energy by oscillating. Where these rubber bands, because they're on a movable object, you could sort of understand that when the spring compresses, when they hit each other and the two rubber bands compress, as they decompress, the car is going to go this way. It's going to absorb the energy of the rubber band's decompression. So the rubber band's going to be oscillating a lot less because you moved the object instead of keeping it in one place and forcing the rubber band to oscillate back and forth. The rubber band was allowed to give the energy to not only shoot the one going this way, but it's able to shoot the one going this way. The thing the rubber band is attached to is now moving. So obviously that's going to absorb its energy. If I move the Newton's cradle as the ball is swinging down this way, I'll obviously absorb all the energy of the ball's motion. So, bullshit. Alright. Enough said. Fuck you some more.